Assalamu alaikum and welcome to another tutorial on EE434. It has been a long time since we have uploaded our lectures. We were discussing about the DC to DC converters and we discussed the basic three converters, which were the buck converter, the boost converter and the buck boost converter. Now before we proceed to the isolated converters, I want to prepare a lecture on the simulation of the converters. So let us start with the concept of the simulation for power electronic converters. We will see what are the two variants that are quite used in the power electronic circuits to understand the dynamic behavior of a given converter circuit, and we will see what are the pros and cons of these two variants, and then we will simulate them, these two variants for a buck converter, to see what are the advantages, what are the pros and cons of each of them. So let us start with the today's class. The very first question that arises is why we need simulation. So there are a lot of advantages of doing the simulation of power electronic converters, but let us summarize only the very few important one. So it provides us a forecast of the system performance without going for the expensive circuitry and expensive measurement instruments. Number two is it gives us the performance analysis with varying conditions. That is, we can see what is the impact of varying the load or varying the source and different values of the components, and we, without developing an actual circuit, we can predict that this circuit will perform in XYZ manner, and also we can predict the dynamic behavior. These are few of the many advantages that simulation provides us. But let us take on to these particular things and we move on to the power electronic circuits. So in power electronic circuits, we have two different types of simulation procedures available. The first one is the switched model simulation, and the second one is an averaged model. Switched model simulation is most widely used. Here we use switches, for example MOSFETs, diodes, BJTs, etc., to simulate the circuits. And it is quite obvious that for a buck converter we will use one switch, one diode, inductor, capacitor and the resistance. So what happens here is that we not only get the dynamic response of a converter, but it gives us a cycle to cycle variation of the current and the voltage across different elements and across different points in the circuit. So this switched model approach is actually, it has various pros and cons. The first one is it gives us a very detailed analysis. And this one is great for transients. However, for this steady state circuits, this is not of much importance, because once the circuit is in a steady state condition, a cycle by cycle or point by point evaluation of a circuit is quite time consuming, and it provides us a lot of limitations to the users. So one of the disadvantage here is that the simulation is time consuming. Average model, on the other side, It is based on the circuit modeling such that the voltage and the currents are averaged. So the average values of these voltage and currents are used to develop an average model. And therefore, this average model development is an interesting topic in power electronic circuits. And we will see in a little bit of in a brief manner that how we can develop an average model for a buck converter. The basic advantage here is that it is not time consuming, yet it gives us important information. But the question is how to develop an average model. Average model development requires a little bit of mathematical analysis of the converters. So for example, let us develop an average model of a buck converter. Now if you see here, this was the basic single pole double throw switch based buck converter. We have this position number 1, we have this position number 2, and this was realized by having a switch here and a diode here. This is Vs, here we have this inductance, here we have this capacitance, and this is the load resistance V0, right? And of course we require to have some gate driver circuit to drive this particular switch Q, and this D actually freewheels whenever we have this Q turned off. Now this is the switch model. Let us develop an average model for this particular converter. Now if you notice that this V0 over Vs, that is the voltage gain ratio, is equal to D, which means that if we have a lossless buck converter, then this is equal to Is over I0. So I can develop a very classical kind of an approach, that this is certainly similar to the concept of the transformer. So in a transformer we have Np over Ns is equal to Vp over Vs is equal to Ip over Is. So this Vp over Vs is based on the turn ratio N. Here it is equal to the turn ratio D. So what I mean to say is that this is quite similar to that concept of a transformer. However, we cannot have an output voltage greater than the input voltage, because this D can have a maximum value equal to 1. So we cannot have a buck converter operation where we have the output voltage greater than the input voltage. However, the concept is quite similar to that of a transformer. So let us move ahead. Using this particular equation number 1, I know that this V0 is the input voltage times the MD, and this voltage transfer ratio MD is equal to D, and therefore V0 is equal to D times Vs, which means, and also we have Is equals to D times I0. This means that if I apply some basic circuit analysis techniques, this means that this output voltage is equal to the input voltage multiplied by a dependent voltage source having a gain equal to D. Similarly, let me write it here. Similarly, the input current Is is equal to the output current multiplied by a dependent current source with a gain that is equal to D. So I can redraw based on these two equations. Based on these two equations, I can say that if for my given converter this is Vs, then this source current Is is equal to D times I naught, where D is the gain of this dependent current source. On the other side, V naught, which is here, is equal to D times Vs. And if we combine these two together, this gives me a transformer equivalent model, something like this one. Here we have this V naught, this is I naught, this is Is, this is Vs, and this solid bar shows that this is actually a DC transformer which is capable of transferring the DC from this input to the output. And this is just an analogy, just an analogy. So based on this particular concept, that we can model a converter using the dependent voltage source and the dependent current source, using the analogy of a transformer, the voltage and the current are averaged, and therefore the output contains the transient behavior. However, because it is averaged, it do not provide us the burden on the computation requirement, and it happens more efficiently and swiftly compared to a cycle to cycle conversion or a switched modeling concept. So this whole concept of using this particular DC transformer model concept, it requires some detailed study, and which is quite an interesting topic for the graduate students. Let us see, for different buck converters, for different converters that we have studied, buck converter, boost converter, and a buck boost converter, that how these models can be developed. So for instance, let us say this is port A, and in port A we have this D times IC. Let us say that we have some sensor here. Using the P-spice analogy, we can use a dummy voltage source here with V equal to 0 to measure the current going to this port C, and here we have a voltage source D times VAP, where this is P. So we need to measure the voltage between point A and point P. If this is a generic model, and that is equal to a box, right, with A, C and P ports available, then for a buck converter, the model is something like this one, that we have this one A, we have this P, we have this C. Here we have the inductance, this is the capacitance, and this is the resistance. So now if you notice here that we are not using the power electronic switches for an average model simulation. We are using these dependent voltage source, dependent current source to evaluate the performance of the circuit, uh, because they give us an average value of the voltage and current on every point or element of a circuit. So this is for a buck converter. For a boost converter, we have this one is C, this is A, this is P. Here we have the capacitor, and here we have this particular resistance, and this is for a boost converter. For a buck boost converter, the circuit can be developed as this one, and we can then simulate the circuit for a buck boost converter. Similar models are available for the chuck converter and other converters as well. So now we have discussed these particular two scenarios. Let me summarize these two simulation strategies. Power electronic circuits can be simulated by using the switches that consist of the diodes and the MOSFETs or some other related switch. However, that cycle to cycle conversion, it gives us a very detailed and a very beautiful information about the circuit transients and the steady state information. But most of the time it is not much required, because cycle to cycle measurements at a steady state value gives us no new information. And therefore, to reduce the computational burden and to reduce the simulation time, an average model is adopted for power electronic circuits. That average model provides us an average value of the voltage and the current in the given circuit. It provides us information about the transients. It gives us the maximum value. It gives us the average value of the steady state voltage and the current. And also, without using the converter switches, which are the BJTs and IGBTs, we use dependent voltage sources and the dependent current sources to simulate this particular thing. Now, these two approaches of simulation can be simulated in PSpice, LTSpice, or any other Spice compatible program. But we will describe this average switching scheme using the PSIM for this particular buck converter, and we will show you that whatever we are getting through a switched model can also be obtained using the average model. So let us now shift on to the process of the simulation, and thereafter we will wrap up this lecture. So this is PSIM, which is a standard power electronic software which is much used. There are student evaluation packages available where you can use, we can download that and you can use it for your undergrad studies or for graduate studies. I have developed two buck converter models. One is a switched model, another one is an average model. The input voltage V in is equal to 10 volt, and with a duty ratio set at 0.2, I am expecting to have 2 volt at the output. Let us first of all simulate this switch model converter, and we see what kind of waveforms we get when we simulate a buck converter using a switch model. So let me simulate this one. So here we have the switched output voltage V naught. As you can see here, this V naught is settling at this 2 volt after having the initial transients. If we zoom in, let me first of all have this. Let me bold this curve here. So as you can see here, I am having this type of an output voltage. About the inductor current, the IL switched is something like this one. So you can see here that it provides us a good information of the transient part as well as the steady state part. And using this whole scenario, I can get a very good type of the inductor current waveform, which gives us a cycle to cycle variation in the system. Now let me introduce you to the average model. Regarding the lecture that I have just given, I have shown you that we require to have a dependent current source as well as a dependent voltage source alongside the inductor, the capacitor, and the resistance and the input voltage source. So here we have this input voltage source. Let me zoom in a little bit. Here we have the input voltage source that is equal to 10 volt. We have a constant, we have a dependent current source available here. This dependent source is available. If you go here, we have this current available, and here we have the voltage gain, voltage controlled or current controlled and the current controlled dependent sources available. So we can use them. This one is a current controlled current source. This arrow sign shows the direction of the flow of the current, and because we are interested in finding out the input, and because we have earlier studied that the input current depends on the output current, therefore I have used a current sensor here, and the current sensor, this input of this current sensor is now connected to this dependent current source. The gain of this dependent source is set to 0 0.2, which is same as that of a duty cycle. Also, we require to have this voltage control voltage source here with the same gain that is set at 0 0.2, and because it requires to have the voltage between this A point and this P point, so we have this VAP available as well. The value of this inductance is 400 microhenry, which is same as that of this of the inductor which is used for the switch model. We are not using any switch here, and let us simulate this particular circuit. So once we have simulated this one, we have this averaged model available. So I will draw the averaged waveforms as well as the voltage waveform for average and the switched circuit. So let me bold these a little bit so that it is more visible. So as you can see here, this red waveform, which is the average waveform, it gives us the average value of the switch waveform, yet it contains the information about the transients as well as the steady state part. This type of a scheme is well known in the power electronic circuits for its less computational burden, as I have explained earlier, and it gives us the same information. So you see here, for this particular for this particular waveform, the information about the cycle to cycle variation is not important for the steady state system. Rather, the circuit can be evaluated using the transient behavior that is well shown by this average value. As you can see here, we have a transient here, and thereafter the waveform is settling at this 2 volt, and this is exactly what was happening in a switched converter. But because of the use of the averaging here, the system provides you the average value of this whole switched cycle to cycle variation. And I hope that you have enjoyed this particular lecture. Thank you very much. Allah Hafiz.